In this video, we're going to take a look at Boolean logic in computer science. So let's think about electronics first. So in electronics, the flow of electricity is controlled using little chips. These are essentially logic gates. So a logic gate has one or more inputs and one output. And the type of output depends on the type of gate and the 6 that we need to know. So for GCSE, you need to know the AND gate, OR gate, NOT gate, XOR gate, NAND and NOR. For most of the GCSE boards, you need to AND, OR, NOT, XOR. Some need NAND, some need NOR. For EDUCAS, it's just the first 4. Now, logic gates are small devices that take a binary input and produce a binary output based on what the input is. And in case of computers, they're incredibly small. They use things called transistors. Now, the output produced depends on the logic gate we use. So there's 6, as I've already said, that we must be able to understand and use, and it's important to understand that logic gates are at the heart of everything that computers can do. So you've got these different symbols. So you've got this triangle is a NOT gate with a little circle on the end. You've got AND, OR, NAND, NOR, and XOR. Now, the NOR gate is the same as an OR gate, but it has a little circle on the end, which is taken from the NOT, and the same with NAND. And then you've got XOR, has a little line underneath it. Now, it's really important you understand what these mean, because they're not going to say NOT gate underneath them, you'll just get the symbols. So first things first, we've got the AND gate. So if input A is 1 and B is 1, then C, the output, is also 1. So it has to be both 1. So if the temperature is less than 0 and the month is December, then it's likely to snow. Something along those lines. So it's where 2 conditions must be true for the output to be true. Next, we've got the OR gate. So if A or B are 1, then C is 1. So if your safe door is open or your security alarm is triggered, then alert the police maybe. So you've got no inputs, so it's 0, but these have got any 1s, so it becomes a 1. You then got the NOT gate, which is just not whatever it is, so it swaps the input. So if it's 0, it makes it 1, if it's 1, it makes it 0. We then got the XOR, which stands for exclusively OR, which means the output will be 1 if it's one or the other, but not both. Okay, so if you've got 2 1s, it'll be a 0. If you've got a 0 and a 1, or a 1 and a 0, it will be a 1. Then we've got NAND gate, which stands for not and both inputs must be 1 for the output to be 0, so it's the opposite of an AND gate. So you've got 0 and 0 is 1, 1 and 0 is 1, 0 and 1 is 1, and 1 and 1 is 0, so it's the opposite. And then we've got the NOR, which again is just the opposite of an OR gate. So both values must be 0 for the output to be 1. So we've got 0 and 0 is 1, then 1 and 0 is 0, 0 and 1 is 0, and 1 and 1 is 0. Now, logic circuits are logic gates that are being connected so that the output is an input to another. So logic circuits can be designed to perform very complex tasks, and each logic circuit has a truth table. Now for the exam, you need to be able to create a logic circuit, you need to be able to create a truth table, and be able to write an expression based on 3 input circuits with 6 gates. Now to produce a truth table, what we need to do is just making one for one gate is pretty easy, we've seen it, we just do the 1. But what we have to do is we have to look at all the inputs, we need to look at all the individual gates and how they connect together. So in creating a truth table for a logic gate, it's desirable to track the intermediate values. So what I mean by that is you do a truth table or a column in your truth table for each individual circuit. So here we've got an example. So we've got an AND gate, we've got a NOR gate, we've got an OR gate and an XOR gate, so we've got 3 parts. And what we need to do is look at our inputs and we start tracking where things are. So you see I've written P, Q and R, these are our intermediate values. So you can see that I've done the AND gate, so A and B. So if that's an AND gate result, we've done the NOR gate, so we've got the Q result. We then look at the R result, and then we look at the final result, which will be the XOR between C, so this one, and R. So C and R, so we've got 1 0 0 1 1 0 0 1, so there's the one or the other, so it's exclusively OR, so the answer would be 1 1 1 1. Okay, so we're going to look at how we go about creating a truth table. So first things first, we take a look at the symbols we've got. So we've got these logic circuits here. So we've got two inputs, we've got A and B. So first we do A, and then we've got B. That's the first we need to do. So first things first, we need to do the input values. So we've got 0, 0, 1, 0, 0, 1, and 1 and 1. Just like that. Okay, so those are our input values. Now the first logic gate we've got is A and B. So A and B. The other one we've got is A or B. So A or B. And then we've got this one here. So what we do first is I usually label these. So we've got A, B, so we've got C, I've got D, and I've got E. Okay, so E, so we've got C, D, and E. Now E is not A or B, so we can just say not brackets A or B. And we've got X here, so we've got X, which is essentially C or E. I'll just finish these lines off. So we've got A and B, or not A or B, like that. Okay, so then we work each one individually. So we work out C, so it's an AND gate, so 0 and 0 0 0 0 1. Now this is an OR gate, so once you learn these, you know you can just look at an OR gate and know it's going to be 0 1 1. Now this is not A or B, so we do the opposite, so it's 1 0 0 0, and this last one is an OR between this column here and this column here. So we've got 0 and 1, so that's 1, 0 and 0 0 0 1, and there's our answer. Then usually you get your marks by going row by row, so the examiner will look around and go, right, that row's correct, that row's correct, that row's correct, that row's correct, and you'll get like 4 marks or whatever the marks are for that question. Now one thing you do need to be able to do is you need to be able to take a logic statement. So I've got A and B, or not AX or B. So what I need to do is I need to create the logic circuit. So we start off with this first part. So we need to have two circuits all together. So first things first, nice and simple. We've got A, then we've got B. Okay, just like that. So we've got A and B. Now one thing I do is I actually write the name of it on it as well, just in case the examiner can't tell what shape you've done, but that's about right. And then that's going to go into something else in a minute. Then we need to do the not AX or B. So what we'll do is do AX or B. So we start off, do the brackets first like you would in maths. So we do just draw your normal OR, and then with your XOR, what you've got to do is you just got to put in a little line underneath your thing like that. Okay, doesn't look great, I apologise. So then we do a little circle like that, and plug that in, and then you do a little circle from the A and plug that in. Okay, so now at the minute I've done this one, I've done this one. So the next thing I need to do is I then need to not it. So I take the result from that and do a not gate. So there's my not gate, and then I need to OR these together. So I just do a normal OR like that, and then and that's it. So you do, just pick a different colour, do this one first, then this one, then this one, then this one, okay? So you got 1, 2, 3, and 4. Okay, and that's it, and that's how you draw a circuit. It doesn't matter if you get a big, even longer one of these, you just got to make sure you're doing each individual circuit at a time and then building it together to make the final result. Now, in real life, logic circuits are built with an actual purpose in mind. So you need to be able to plan a logic circuit that will solve a real world problem, such as when to set off an intruder alarm. So here's an example. So I've got 3 different statements. So if the turbine speed is less than or equal to 1000 RPM and the bearing temperature is greater than 80 degrees, or the turbine speed is greater than 1000 RPM and wind velocity is greater than 120 km per hour, or bearing temperature is less than or equal to 80 and wind velocity is greater than 120. So I've got these values here. So if the turbine speed is greater than 1000, the binary value is 1. If it's less than or equal to, it's 0, and so on. So the first things first, we need to convert these into logic statements. So the turbine speed being less than or equal to 1000 and bearing temperature greater than 80 is not S. So if you think this is S and the 0 value being a not S, so we've got X equals not S and T. Okay, so the 0 and the 1. Then turbine speed is greater than 1000 RPM and wind velocity is greater than 120. The statement is S and W, so it needs to be this one and this one, so it's a 1 and a 1, so it's just S and W. And the bearing temperature is less than or equal to 80 and the wind velocity is greater than 120, so it's going to be this one here, so not T and W. So we've converted them into different statements. Now what we need to do is create an intermediate circuit. So the X equals not S and T, so we've got a not gate on the S and T. Then we've got S and W, so it's just an and then this one is not T and W, so it's similar to the first one. And then we put the whole thing together because it's joined by an OR. So then we join the first 2 statements, this OR, like this. And then we have the final circuit like that. So now we've got a full circuit based on all of those values. And then once you've done that, you need to produce a truth table, and then we can use logic statements to help us do it. So these are just the ones we've made up earlier on. So S is not 1 and T equals 1, S equals 1 and W equals 1, and so on. And then we prove that we're correct by looking at these values. And if X becomes the correct value,
a real life situation,
you've done the
so
logic circuit.
You might get a question like the one I'm about to say. So in the system, there are 3 switches and an alarm. So we've got an alarm, and we've got 3 switches. So we're going to call switch A, B, and C. So we've got switches A, B, and C. So we've got 3 inputs. Now, the alarm will only sound if switches A and B are on. So the alarm's going to sound if A and B are on. If switch C is on, then the alarm will stop, okay? So we think about how we go about this. So if A and B are on, it's going to turn on, and if switch C is off. Now if we're saying A and B, we're sort of saying A is on and B is on. So if we said A is on and B is on and C is on, that would be wrong, because we're saying that if you press in A, which is right, pressing B, that's right, pressing C, it'll turn on. So it needs to be the opposite. So if you press in A switch and you're pressing the B switch and you're not pressing C, okay? So that is our logic statement. So we've got, you're pressing the A switch down, you're pressing the B switch down, and you're not touching C, then the alarm will go off. So that's our statement so far. Now, the next thing you need to do is we need to actually create the logic statement, the circuit, sorry. But the best thing to do first is to test you're correct, because things go wrong. So we draw out our truth table. So we've got A, we've got B, and we've got C. Easiest way to do it, if you've got 3 inputs, there needs to be 8 values. So 0, 0, 0, 0, then 1, 2, 3, 4, that's 1, and then we do 0, 0, 1, 1, 0, 0, 1, 1, because basically we need every combination to test our theory is right. And then we can do 0, 1, 0, 1, 0, 1, and 0, 1. So those are our inputs, like that. Now first things first, we need to do A and B. Now some people can just look. They can just look at a logic gate, or look at a circuit, or look at a statement and just know what's going to happen. I can't do that. I think it's best to work through it all, but it depends on how you work. So it's A and B, so we've got 0, 0, 0, 0, 0, 0, 1, and 1. Okay? Now, not C, it's just the opposite of C, so we've got not C, so it's just the opposite, so it should be 1, 0, 1, 0, 1, 0, 1, 0, that's that done. And now we need to combine them together, so we need to do an AND between these two. And that's going to be the alarm, or X. So we need to AND these two together. So I've not pressed those switches, but I have pressed these not switch. So we've got a 0 output there, a 0 output there, 0, 0, 0, 0. Now, because it's an AND, these I've not pressed switch A and B, so I've not tried to set the alarm off. Whereas here, it's a little bit different now. Because now I've pressed the alarm, but I haven't, here I've not pressed the switch, okay? So I'll admit it, that's not on. Because it's a 1 and a 1, that means we've got a 1 there, and then this one, I have pressed the switch, so it's 0, so that makes sense, that's correct. Because I've turned switch A on, I've turned switch B on, but I've not turned switch C on. So you can see here, that is our perfect criteria where the alarm should go off, where A is on, B is on, but C is off. Whereas the one underneath it, C is on as well, so that's why we're knotting it, because otherwise it wouldn't make sense. Now the last thing we need to do is we need to draw the circuit. So again, just like before, you've got your 3 inputs. So we've got A, B, and C. Now the first one's a nice AND, and then we've got not C, and then we're ANDing them together. So we should do another AND, and then that goes into there, and then the alarm's there. And then just to make sure you don't get anything wrong, just write and then no. Yeah, and that's it, and that's the question done. So in the system, the 3 switches, the alarm will only sound if switches A and B are on, and if switch C is turned on, then the alarm will stop. Now hopefully you found that really useful and you found the exam questions quite insightful. If you did, please make sure you like and subscribe, and I will see you in the next one.